So in any case, that is here, the constant temperature means N is equal to 1, and the temperature T1 is going to become T2, and you can also call it as a hyperbolic process, right? So this is the isothermal process. Isothermal, this is the expansion. But here observe that this is the thing. So this is the isothermal expansion. So the isothermal expansion, right? PV is equal to constant. PV is equal to constant. So this is the isothermal expansion. That is where N is equal to 1, and this is the expansion process. This is the expansion process. So in the same way, you can write it the compression process, right? So PV, right, and this one some curve type 1 to 2, PV is equal to constant, and this is the area in the flow work, and this is the compression. This is the compression process. So this is the compression process, and the student has to observe this particular compression and isothermal compression and isothermal expansion. So he must be very careful about this particular writer. Now here, what is that? The applying the first law of a thermodynamics, that is Q1 to 2 when a system changes from state 1 to the state 2. This is delta H, right, plus W 1 to 2. Now this W is nothing but equal to minus of VdP when a system changes from state 1 to the state 2, and we know that PV is equal to constant. What is here? This V is nothing but C by P. V is nothing but C by P. That you need to substitute over here. Minus 1 to 2. V is nothing but C, and this is nothing but dP by P. This is nothing but dP by P. So when you remove the integral, right? So this is C. Then what you will get? Then you can get it as a ln P, and apply the limits 1 to 2. Then it is a minus C ln P2 minus ln P1. So when you remove this here, minus C ln P2 by P1, and remove this minus sign also. So constant C ln P1 by P2. What is the C here? This C is nothing but when a system changes. So either it is P1 V1, that is nothing but equal to P2 V2. So you can apply here that C is nothing but P1 V1 ln P1 by P2. What about this P1 V1? That is nothing but equal to MRT1 ln P1 by P2, right? In another words, where it is W is equal to, so it is in terms of the volume. So when the pressures are given, then it is okay. But sometimes you are going to get the volume P1 V1, you will get in terms of volume P1 V1 ln. So here it is V2 by V1 because the pressure and volumes are inversely proportional. So that is nothing but equal to MRT1 ln V2 by V1. So apply the first law of thermodynamics, because in a isothermal process delta H is 0. Why? That here that delta H is equal to Cp T2 minus T1. Since T1 is equal to T2, delta H is equal to 0. Delta H is equal to 0, right? So, but ultimately the heat transfer Q is equal to nothing but W is nothing but equal to, so P1 V1 ln V2 by V1, that is nothing but equal to MR T1 ln V2 by V1. So this kind of expression is valid because you have got the same thing. This kind of expression is valid both for open and closed system. Open and closed system. So sometimes they may ask, prove that heat and work transfer for the case of a flow and non-flow process as this one. Prove that heat and work transfer for the open and closed system as P1 V1 ln V2 by V1, that is nothing but equal to MRT1 ln V2 by V1. So only this particular expression is going to be valid for the open as well as closed system. So every student has to observe this particular information, right? So when you mention, if you get the numerical problem in terms of the pressure, then you have to use this expression. If you get the numerical data as in terms of volume, that is V2 by V1, then you have to use this particular expression, right? So this is Q is equal to W is equal to P1 V1 ln V2 by V1, that is equal to MRT1 ln V2 by V1. So finally, you can use this particular expression for constant temperature process. This is how you have to derive the equations. This is how you have to derive the expression, right? So this is the isothermal process where the temperature remains constant. Next, there is the isentropic process is there and the polytropic process is there. So every time, if you watch the video, then if you take the notes and you write it in your notebook sequentially, right, and you can get the good information. That means you are going to become the confident while solving the numerical problems or also developing the expression to this particular thermodynamics for various process. So the constant temperature process is over. Constant temperature process is over, right? Next one is the adiabatic process. So later we will discuss that polytropic process. So this is the adiabatic process. Isentropic process, or you can call it as a reversible adiabatic process. Reversible adiabatic process. Reversible adiabatic process. So it is represented as Pv to the power of gamma is equal to constant. Pv to the power of gamma is equal to constant, right? So this gamma is nothing but equal to Cp by Cv. That gamma is nothing but equal to Cp by Cv. So this is nothing but a property. You can call it isentropic index. Isentropic gamma is nothing but isentropic index. This gamma is nothing but isentropic index. Reversible adiabatic process, right? Now here apply the first law of thermodynamics, that is Q1 to 2, that is nothing but equal to delta H plus W. W1 to 2, right? So now here P1 V1 to the power of gamma is equal to P2 V2 to the power of gamma is equal to PV to the power of gamma is equal to constant. Then what about the work? So this work is nothing but W1 to 2, it is 1 to 2 VdP. So it is minus VdP, right? So this is the standard one for open system. Closed system it is PdV. Closed system is PdV. Open system is minus 1 to 2 VdP, right? So this one here you can consider as in this fashion, whatever the notations you are following. So this. So what is this V? V is nothing but equal to, yes, C by P to the power of 1 by gamma, right? So that V is equal to C by P to the power of 1 by gamma. Then you have to substitute that one. So that is 1 to 2. That specific volume is nothing but equal to C by P to the power of 1 by gamma into dp, right? So then keeping this C to the power of 1 by gamma, C to the power of 1 by gamma, integral 1 to 2, and this is P to the power of minus half dp, right? Or in this particular work side, right? So this is P to the power of minus, it is minus P to the power of minus 1 by gamma. I'm sorry, P to the power of minus 1 by gamma, right? So integrate this particular case. So when you integrate, that is equal to W1 to 2 is equal to, when you integrate that one, C is nothing but, let me write it as a C to the power of 1 by gamma, that is equal to P to the power of minus 1 by gamma plus 1 divided by minus 1 by gamma plus 1 following the limits as this one. So when you follow this particular thing, so C to the power of 1 by gamma into, and now here you will get as P2 to the power of minus 1 by gamma plus 1 minus P1 to the power of minus 1 by gamma plus 1 divided by minus 1 by gamma plus 1, right? So now you remove this one. So whatever the constant, that is, let me write as P2 V2 to the power of gamma to the total, it is 1 by gamma into P2 to the power of minus 1 by gamma plus 1 minus P1 V1 to the power of gamma, right? And whole power, it is to the power of 1 by gamma, P1 to the power of minus 1 by gamma plus 1 divided by minus 1 by gamma plus 1. So now there are certain things which are going to be cancelled, because this is here, you observe that one. This P2 1 by gamma and this one, right? So you will get as in this. So here also P1 to the power of 1 by gamma and this P1. So finally, what ultimately you are going to be getting is, when you solve this particular issue, that is gamma by gamma minus 1 into P1 V1 minus P2 V2. So this is the flow work for the open system, right? This is for the flow work for the open system, right? Gamma by gamma minus 1. So this is for the open system. And if you recapitulate the closed system, if you recapitulate the closed system in case of a adiabatic process, that is W1 to 2, what is the expression? You will get the expression as P1 V1 minus P2 V2 divided by gamma minus 1. So only the expression is for the open system, you will get it as gamma by gamma minus 1 into P1 V1 minus P2 V2, right? So this is nothing but this particular. And here, in terms of this case, that is, let me erase some portion here. So as we all know that in terms of the temperature, what you are going to write? So that is W1 to 2 in terms of temperature. There the volumes are given P1, V1. But if you observe that, sorry, gamma by gamma minus 1, that is gamma by gamma minus 1 into MR T1 minus T2. Gamma by gamma minus 1 MR T1 minus T2. And there is the enthalpy is also there. So that enthalpy, that is the change in enthalpy, that is equal to, here the M is there, so I can also consider MCP T2 minus T1, MCP T2 minus T1, right? Then we all know that this CV is equal to R by gamma minus 1. CP is nothing but equal to gamma R by gamma minus 1. So substituting, so if you bring all these particular terms to this particular connection, then you will get the expression for this particular case, right? So try to work it out for the heat flow rate. So that is what is the heat flow rate that you are going to arrive. So I have given the enough information. So whether you are applying in terms of gamma by gamma minus 1 into MR T1 minus T2, and this delta H is equal to MCP T2 minus T1, that Cp is nothing but equal to gamma R by gamma minus 1. And finally, what is the expression that you are going to get? So isentropic means entropy remains constant. Isentropic means entropy remains constant. So that things the student has to understand. So here, and the drawing the PV plane, that is also important. So you should not forget that